Okay, I think we can start. Um, so yeah, so today we are going to talk about representations of groups. And so let me define what that is. Um, so definition, and it's like a general definition. There's more specific definitions for various cases. Let's say, so a representation um, of a group G on a finite dimensional vector space V is a group homomorphism rho from G to the space GLV, space of invertible linear transformations on V. So in this case, we call the vector space V is called a G module. Okay. So, and a thing to note, sometimes it is fairly clear what rho is, or maybe we're talking about some something that applies to all representations for a given group in V, or like when the choice of rho is unambiguous. When rho is unambiguous, we can also say that V itself is a representation of G. And in that case, so yeah, when rho is unambiguous, we say V is a representation. Oh my god, my handwriting. Representation of G. And we write I'm trying to let me pick a different piece of chalk. We write G acting on a vector V instead of rho of G acting on V. I'm sorry for the horrible handwriting. But yeah, this is, when rho is clear, that's what we do. So now a couple of examples of representations. So first of all, there is the trivial representation for any group V, vector space V, the trivial representation which is just rho sends every element of G to the identity map. Clearly this is a group homomorphism, right? Then there is, let's see, I have in my notes, I have, yes, sure. If we pick a vector space V, there is a nice group homomorphism from GL of V to itself. Right? So this is our group, and this is like GL of V from the vector space given by rho of T is T. Okay, so in this case, rho is the identity. For finite groups, or yeah, sure, let's do finite groups. Let's look at the symmetric group for Sn. There's two nice representations that one can think of. So first of all, if you have, say, a one-dimensional vector space, let's say, on C1. For finite groups, you usually want to look at complex vector spaces, or at least that's what Fulton and Harris do, because there's like lemmas that are nice. And so on C1, you can have rho sending a permutation sigma to multiplication by sine sigma. So I suppose it would be nicer to write this as rho of sigma z equals sine sigma z. Okay, so it's just multiplication by like 1 or minus 1, depending on what permutation it is. And then on Cn, well, you know, what is Cn? It's like an ordered list of n entries, and then our members of the permutation group, they permute sets with n entries. So what do? So you have, okay, so what does if I have a member sigma of Sn, what does it do? If I have like sigma from the set 1 to n, this is a permutation, right? So this is a bijection between the set and itself, right? Hello. He's gone.
He's not here.
He's not here.
I won't be here.
Okay. So, right. So maybe it, you know, you have 1, 2, 3 goes to 3, 1, 2. Yeah. Now, and let's say you have a vector ABC, right? And you want to somehow have like a nice map that, like, what's a natural way for this permutation to act on this vector? Sorry? Exactly. Yeah, it permutes the entries of the vector. That's precisely what it does. So yeah. Let's see. So rho sigma is given by so rho of sigma of Ej is equal to E sigma j, right? Yeah, I think so. There was a few examples, and of course, I mean, we covered earlier certain Lie groups, you know, like SU, and that obviously acts on, so like, I suppose it would be, well, yeah, Cn by just these are the matrices. It just acts on it the way that you would expect it to. Anyway, sorry.
For Lie groups, you want.
Yeah, we'll talk about Lie group homomorphisms in a second. I want to do a bit more. Actually, we're going to talk about finite groups a little bit, and then we'll talk about Lie group homomorph. Actually, how do I? Yeah, sure. I don't know what the point of that was. Anyway, I'm gonna erase this now. Okay. So right. Yeah. Let's see. I want to talk a bit about subrepresentations. So a subrepresentation of, let's call it W, of a representation V is a subspace of V, which is invariant under G. So what does this mean? So suppose, rho is the map from G to GLV. This means that, for any element of G, we have rho and any element W of the subspace. We have that rho of G of W is again in W, right? So it's just W is invariant under rho of G for any G. That's essentially it. That's what it means to be invariant under G. Now, okay, question. Why does this definition make sense? Why do we call this a subrepresentation? It's a subspace, right? But the word subrepresentation kind of implies or maybe suggests that W is also a representation, right? Yes. Why is that so? Yes, what kind of homeomorphism is there from G to W? How do you have this map, but it's between G and GL of V. Ideally, we want some like rho prime from G. Yeah, exactly. And how does, well, W is invariant under rho of G. How does that help us maybe in some way? Well, okay. When you have rho of G is an invertible linear operator, right? When you have, let's say I have an invertible linear operator T, and I have some W under which T is, or W which is T invariant. Sorry? I can't hear you. Yes. And okay, I'm just going to say it. Furthermore, we can restrict T to W. That's sort of the idea. And it will be an operator still. That's the point. Because if it's not invariant, then there's maybe some element of W that gets mapped to outside of W, and it's no longer like an operator, right? So yeah, but since W is invariant under G, we can just take like rho prime of G equal to rho of G restricted to W, okay? And so that's the nice, yeah, that's why it's a subrepresentation. Okay, right. So a representation is called irreducible if it has no non-zero proper invariant subspaces. In other words, if it has no subrepresentations, essentially, that are not just like the zero subspace or itself. Okay. Yeah. And in the case of finite groups specifically on vector spaces over a field of characteristic 0, there's this very nice result. I suppose I should first say there's still a bit of work to be done. So before we get to that result, a direct sum. So we know, actually, we might not know what a direct sum is because there's two different definitions. So, given vector spaces V and W, we can define the direct sum of V and W as the set of these ordered pairs. It's essentially like the Cartesian product, but with a linear structure attached, such that V is in V, W is in W, and then we can have like lambda of V comma W is just, it gets distributed over the entries, and then, addition is coordinate-wise. That's the definition that Fulton and Harris uses. Yes. And, if you look at this and you look at representations and you think, well, okay, suppose I have a representation on V of G, and then I have a representation of the same group on W. It seems like there's a very easy way to get a representation on the direct product of V and W by just like, so if G acts on V and W, which is the same thing as has representations, then define so yeah, let's just do this. G of V comma W as it just acting separately on the two entries, right? So this should make sense. And this is in fact a group homomorphism. And it does in fact give linear maps. And life is good. Now, here's sort of the idea. I'm going to erase this. So, it would be nice to think of to somehow classify the representations of a group on a given vector space. And one way to do that would be to kind of think of the vector space as being composed of various smaller vector spaces through algebraic operations such as the direct sum. It'd be very nice if we could have the vector space be some decomposition of irreducible representations. And that is precisely the kind of situation that we get with finite groups over finite dimensional complex vector spaces. And so let's quickly prove that result. So proposition, if G is finite, V is a complex finite dimensional vector space. Rho from G to V is, yes? Oh, sorry. GLV. GLV is a representation. And W is a subrepresentation. Then there exists a G invariant subspace. Let's call it W prime, yeah. Such that V is a direct sum of W and W prime. Okay. Sorry, what do you mean? What does the equal sign mean? Well, I mean, I suppose you could say isomorphic.
You could say isomorphic, or you could just replace the direct sum with an ordinary sum.
That is true. Or I mean, you could also say it's a direct sum in the other sense, where it's just a sum with them being disjoint. Such that, yeah, with, as a note, this being disjoint sum. Okay, right, yeah. That's, see, like, Fulton and Harris doesn't call it that for whatever reason. Yeah, I don't know. Anyway, so how do you do this? It's a rather interesting construction. So first of all, proof. What we do is we construct an inner product on, or well, an inner product kind of on the finite dimensional vector space. It's kind of because it's a symmetric bilinear form. It's not you know, it's not, it doesn't have the conjugate stuff going on. So first of all, let beta be a, let me say, positive definite symmetric bilinear form. Or, well, is that, yeah, yes. They call it a Hermitian inner product. So why can we say this? Well, we can pick just any basis in VC, or yeah, in V, and then say that, oh, this basis is orthonormal now. I declare it to be orthonormal. And then that's going to be just having like beta of, so like say EI, comma EJ equals delta IJ.
So one is Hermitian metric, then one is be bilinear. It is S-linear.
It should be what?
S-linear. Linear in one argument and n-linear in the other.
Well, well, they do. I'm not sure if they actually.
Doesn't make sense for the bilinear form to be positive net.
Ah. Okay, yeah.
Positive, the beta of IV, comma IV is not negative.
Okay. I'll just use what they say, which is Hermitian inner product. But yeah, the point is, you can just pick a basis, say that it's orthonormal, and then that gives you what you want. So yeah. Now what we do is we define a second Hermitian inner product, beta prime, of V comma W by just averaging over all the elements of G. We can do this because G is finite. We take, so beta prime of V and W is equal to beta of the sum over all G of beta of, I guess I'll be proper and I'll write rho of G V, rho of G W. Okay. Why do we do this? Well, observe beta prime of G. First of all, this is also a Hermitian inner product. You can check, you can convince yourself. Second of all, if I have, if I act on both V and W with G, that is not going to do anything to my inner product. So beta prime of G acting on V and G acting on W is the same as beta prime of V and W. That's important for us because now we can say, now take, so the orthogonal complement of W as our W prime. And this is going to be invariant under G because, so suppose with respect to like beta prime now. Why does this work? Why is this, a direct sum? So let's say we have, so yeah, let W, let U belong to the orthogonal complement. So what does this mean? This just means, again, beta prime of U of W is equal to 0 for all W and W. Then we use this fact. This implies that we can just multiply everything by G. So we have rho of G of U, rho of G of W, and this is again equal to 0 from here. But then for all W and W, but then the point is this is an invertible linear transformation, which is invariant on W, which means that this is true if and only if beta prime of rho of G of U inner product with W is equal to 0 for all W and W, which is the same as i.e. G of U is again in the complement, which is to say the complement is G invariant, right? Because I mean this is invertible, so we can always just take like W prime is equal to the inverse of this times W and then substitute it in, right? So that's the proof. You have, if you have a representation and a subrepresentation, then you can like split it into that subrepresentation plus some other subrepresentation. So, and V is finite dimensional, so you can keep doing this until you arrive at a bunch of irreducible subrepresentations. So, corollary, V can be decomposed. Oh my god. Oh, okay, it's fine. Into irreducible representations. And actually, a similar fact to this corollary is true for compact groups, but not for all groups. Yeah, that's what I'm going to say. That's all I'm going to say. I'm going to erase this. Now, let's talk a tiny bit about maps between representations, and then we'll prove Schur's lemma, and then we'll finally talk about Lie groups. Okay. Sure. Yes. That's so. So like one example is, so R, the additive group, acting on, oh gosh, it was R2. where rho is given by, so it takes, a real number, and then it sends it to this matrix. Oh. And then you can check that this is, in fact, like if I have like a plus b, this will be sent to 1 a plus b 0 1, which is equal to just composing these matrices. You can check that these two linear transformations are equal. So it is in fact group homomorphism, but it has no, oh gosh, the corollary doesn't hold for it essentially. And that's the example.
Why is this not useful?
Because, let's see. See, I saw the example and I wrote it down in my notes, but I didn't think about it very hard. But
useful representation, sub-representation, when your matrices, your representation, turn out to be upper block, upper triangle. Here we're dealing with an upper triangular representation, upper unit triangle. And the first basis vector, in fact,
it is, yeah.
It does nothing to the first basis vector. What happens to the second basis vector? Just gets,
well, it multiplied.
Gets moved along the direction of the first basis vector.
Yeah.
It's dragged.
It's like, and then it's like, no, yes. It's like this, and then it's like a, wow. Yeah.
The point is, the span of the first basis vector is a sub-representation, but you cannot hope to find a complementary sub-representation because, well, a complementary subspace would have to be a line which is not the horizontal line. But any line that is not a horizontal line could not be invariant under this representation, under this section, because it will be also, the representation will necessarily tilt it in the direction of the first basis vector. And that, by the way, is not, the problem is not that we're considering a real representation on the real plane. Because the same argument as presented here works for the real numbers as well. Right? You just need to take the Euclidean approach. This is rather because the group of real numbers is not.
Okay. Yeah, that's what. Yeah. Cool. Okay. Yes. Now let's talk about maps between representations. So, a map. Oh. Yeah. Okay. Yes. No. forgot. Yeah. A map between two representations. V and W is a linear map phi from V to W, satisfying and then I'll be explicit here. Rho W of G of phi of V is equal to phi of rho of V of V, which you can write also as G of phi of V is equal to phi of G of V. So yeah, so it's a linear map that plays nicely with group actions. So phi is also called a G linear map. That's what Fulton and Harris call it. Okay. And again, in the case of finite groups on finite dimensional complex vector spaces, and probably this can be generalized to some extent, there's this nice result, Schur's lemma. So let I mean, sure, I suppose we can, there's a note I wanted to say, but it's a part of the proof, it's fine. Let V and W be irreducible representations. And then let me actually check. Let's see. Yes. So let them be complex, irreducible representations. And then phi be G linear. Then phi is either an isomorphism or the zero map. And second, if V and W are the same map, or the same vector space, then phi is just multiplying something by a constant, or the constant. It's like some complex number. Okay. So I think I'm going to erase this.
Two maps from V to W.
Then they are constant multiples of each other. Yeah.
One of them is scalable.
Oh yeah. Okay. So first of all, observe, and I mean this is kind of true just in general, that if phi is G linear, then the kernel of phi and the image of phi are subrepresentations. Right? So they are invariant under G. And this kind of follows from the fact that phi plays nicely with group actions. So it's not very hard to see. I'm not going to prove it, but it's fairly straightforward. So, and we know that since V, and then we have like the kernel is a subspace, of course, of V and W, of which the image is a subspace, are irreducible. It follows that we have, the kernel being a subrepresentation, being a G-invariant subspace, is either equal to 0 or the entire vector space. And again, the image is equal to either 0 or the entire vector space. So, I mean, clearly, if the image of phi is equal to 0, the 0 vector space, that implies that the kernel of phi is the entire vector space, right? And then if the image phi is not, is not the 0 vector space, then it's equal to the entire vector space, then clearly it can't be the case that the kernel of phi is all of V, so it must be the other option, which is that it's injective. And so, so in the first case, we have that phi is the 0 transformation, and in the second case, we have that phi is an isomorphism. It's injective. So yeah, those are the two cases. And so there we have it. Phi is either an isomorphism or it's the 0 linear transformation. So that's 1. 2, okay. So consider, since we're working over C, phi has an eigenvector, right? Has eigenvector V with eigenvalue lambda. So we have that phi minus lambda I has non-zero kernel. Okay, what what can we say about phi minus lambda I? What else can we say about it? In particular, something about how it interacts with G, maybe. Or some nice property. No? Okay. Well, we know that phi is G linear, right? So it plays nicely with the group action. The identity, what can we I mean, you know, maybe unsurprisingly is also G linear, right? So it's a combination of them. This is also going to be G linear. This is also going to be a map between representations. Now, refer to one, a map between representations, in this case, oh, sorry. Yeah, because it's the same is over, I'm sorry. Yeah, it's a linear operator. Anyway, so yeah, it's a map between representations. Maps between representations, between two irreducible representations in this case, are either isomorphisms or they're zero. This is not an isomorphism because it has a non-zero kernel. What's the other option? It is equal to, it's the zero map. Yeah. And so phi is equal to lambda I. Cool. That's Schur's lemma. And that ends our discussion of finite groups. Cool. Now let's talk about Lie groups. Oh, well, I mean, that's true. Yeah. Yes. So a Lie group homomorphism. Lie groups. Is a Lie group representation is what I'm looking for. Is a smooth map from a Lie group. A smooth homomorphism, in fact. From a Lie group G to, well, GLV for some vector space V. Right. Now, so this is a smooth group homomorphism. And recall what we've been talking about for the past few lectures. That we have, if your homomorphism is nice enough, so if I have a connected Lie group, connected Lie group G and a Lie group homomorphism, which again is just like a smooth group homomorphism, rho from G to H, which is some other Lie group. Rho is determined uniquely by D rho at the identity. And so what we can do is, instead of looking at, you know, Lie groups and these smooth maps and this complicated stuff, we can do what we've been doing this entire time, and look at representations of Lie algebras. And so a representation of a Lie algebra how do you write it? It's like, sure. Representation of a Lie algebra G is a linear map so sure, let's also call it rho, from G. See, I can't write it. I'll just use this one. To the endomorphisms of a vector space V. So these are, you know, all the linear transformations, not necessarily invertible from V to itself. Is a linear map satisfying let's see. Is there anything? I remember the second condition, but I do not remember the first. Where is it? Well, yeah, there is no second. Okay, the first condition was that it is linear. Yeah, so that's, yeah, satisfying rho, which is just like, well, I mean, yeah, it's rho of the commutator is equal to the commutator of these two. Or, well, I mean, not the commutator, but the Lie bracket. The rho of the Lie bracket is equal to the, in this case, yes, the commutator of these two matrices, or linear transformations, taken separately. Yeah. Okay. So I guess, do we have to, I mean, I could do like a little recap of what the exponential map does. Is that a good idea? Yes, that is probably a good idea. Why do we want to look at the representations of Lie groups? Well, you know, if you remember last time, we were talking about the exponential map. And an important property of the exponential map was that if you take, so if I have, a Lie group homomorphism from G to H, then in fact, rho of the exponential map of X is equal to the exponential map in H of the push forward of X, which this is just fancy notation for the tangent map, which is the derivative, which is yes, for X in the Lie algebra. Okay. So essentially what this means is that, for my left invariant vector field and for a solution to that vector field, it doesn't matter whether I, generate the vector field in G and then find a solution and then map it using the homomorphism to H, or if I take the vector, push it forward, then generate the vector field, then generate the solution. It's going to give me the same curve. So maybe if I draw a picture, recall, so this is the identity, this is again the identity, this is our G, this is our H, this is rho. So I have this vector X, and then, under the tangent map, it's going to get mapped to some like rho push forward of X. And so recall what we did was we took this vector and essentially like pushed it around using the left multiplication tangent map. So it's, in a sense, we just kind of like duplicated it all over the Lie group to get some kind of vector field. And then we generated a solution for that vector field to flowed along the solution for 1 unit of time, and that was the exponential map. What this is saying is essentially I could do that and then take it over to H. I could do the whole process here and then map it to H, or I could take this vector, move it to H at the beginning, do the whole process here, and then I'm going to end up with like the same thing. That was the claim. Cool. Now, you might notice GL of V, if we take, say, Rn or something, GL of V is, it's a Lie group, right? It's a Lie group, so a representation is going to be a Lie group homomorphism, such as this, which means that this also applies in this case. Now, the nice thing about this whole thing is that we actually know how to exponentiate things in GL of Rn. It's literally just, so like, if I have rho from my group G to GL of Rn, then we saw in last lecture that, I'm going to have the exponential map here is literally going to be just exponentiating the matrix. I guess I should write it as like rho push forward X. Yeah, this is literally just going to be like a sum of like whatever it was, k factorial x k from 1 to infinity. And so we can calculate things here. That's really nice, and that's why representations are cool, I think. Yes, that's the recap, and then let's do an example and finish. Yeah. Yes. So it's very, very simple, very familiar example. Let's take S1, which is like, I mean, you can also call it U1. This is like, it's the set of all rotations in 2D space. So I'll call it S1. Call it S1, and we're going to think of this as the set of all complex numbers such that they have absolute value 1. Okay, this is just a circle. Now this is a group under multiplication. What we can do is we can consider S1 acting on C. Okay. And in particular, let's take rho as taking some element Z. I don't like that actually. Let's use G just to be just to make it more clear. But all of these are complex numbers, right? So it takes G and it quite literally sends it to multiplication by GK. How do I write this? I guess the 1-by-1 matrix that is multiplication by G to the power of K. Does that make sense? This is a complex number. It sends it to a 1-by-1 matrix, which is just the complex number to the power of K, where K is some integer. Yeah. So this, the most usual case is that K is equal to 1, but other coefficients also work. It's also a valid way to represent the group. And in fact, you can prove somehow that these are all the possible representations, or at least that's what Ivan said. So yes. So that's our Lie group homomorphism. It's good and all. Now, let's look at the Lie algebra, sort of Lie algebra representation. So we have, first of all, we need to parameterize our S1. So what we do is we take a map. So we think of this as, I don't know, let's say G. No, definitely not G. F of theta gives us e to the I theta. we want, it doesn't really matter. It doesn't really matter because we are just taking the derivative of the identity, so it's fine. So yeah, so, and what we do now, is we take, so rho of f, and we think of kind of, am I doing this right? I think I am. Yes. So we differentiate it, because again, the Lie group homomorphism, or the, yeah, the linear map that you have for the Lie algebra homomorphism is like uniquely identified with the Lie group homomorphisms by the derivative of that Lie group homomorphism, Lie group representation. Anyway, so you take the derivative, it gives you like, in this case, the derivative of ei k theta, which is ik. Oh yeah. And so that's sort of our Lie group, or Lie algebra representation, that we have, we have the tangent space, or well, we have sort of the space where theta lives, and then we have some kind of vector x here, and then it's going to get sent to d rho is going to get sent to the tangent space of the identity, some vector here. And that's, I think, that's it. I think that's it. Okay, cool.
Could you give an example when Lie algebra representation, where the Lie algebra is the Lie algebra of a given group, does not actually come from the representation of
No.
you know, Pauli matrices.
I do not know Pauli matrices.
There are three notable two adjoints 2 by 2 complex matrices. You can write them down. One of them is 0, 1, minus 1, 0. The other one is 0, I, 0. And the third one is I, 0, 0, minus I. So these are called Pauli matrices. Okay, and it turns out they satisfy the commutation relations. That if you take two of these matrices and you commute them. So right. So first of all, the three of these matrices, they're called sigma ones. So if you take any two of these matrices, they always anti-commute. So that you don't have to for I not equal to k. That's one. So in particular, if you want to take commutators, two of these matrices, that's the same after a factor of 2. That's the same as just taking the product. Just multiply it. And it turns out, as you can check, again for I not, as you can check, the product of 2 of these matrices will give you the third matrix. Up to a sign. Depends on the order in which you multiply them. So in fact, the commutation relations here are that the commutator of 2 different matrices gives you the third matrix up to a sign, up to a factor of 2, which you can diffuse by multiplying each one. So, okay, so these commutation relations turn out to turn the space spanned by these 3 matrices into a Lie algebra that is isomorphic to the Lie algebra SO3. The Lie algebra of the Lie group SO3 of special orthogonal transformations. Because the Lie algebra SO3 also has 3 generators. It has 3 basis vectors, where the first one is rotation in the xy plane, the second is rotation in the yz plane, the third is rotation in the zx plane. So these are exactly, if you take that basis in SO3 and take this basis in this Lie algebra, and you send one basis to the other, that will be an isomorphism of Lie algebra. So in fact, these 3 matrices, so what I just said both terms of these 3 matrices give you a representation of SO3 on the 2-dimensional complex vector space of the Lie algebra SO3. This is called the spinor representation of SO3. And it turns out the spinor representation does not actually integrate to a representation of the Lie group SO3, because in SO3 there's an element, well, in fact more than one element, but there are elements that you can represent as exponential of some Lie algebra elements in more than one way. And if you take 2 of those ways, they won't give you the same matrix. Once you exponentiate in, so if you use your formula, right, define the representation on the exponential of x as the exponential of the matrix corresponding to x. So it turns out these 2 exponentials of the 2 matrices you get by looking at 2 different vectors have the same exponential in G, in SON, in SO3. These 2 matrices will differ by a sign. So the representation will not be uniquely defined. That is the spinor effect, where you can, sometimes it's phrased as, you can turn 360 degrees and not return to where you previously were. You'll return to minus where you previously were. That's this effect. This SO3 this representation of the Lie algebra SO3 does not integrate to the but it does, however, integrate to the Lie group SU2, which is the universal cover of the some